up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue to look and explore exponential functions. Today we are going to try to get into some applications of exponential functions. Now, exponential and logarithmic functions, which is what we are focused on this unit, we will find later will have some of the most broad applications to real life that we see in Algebra 2 until we get to probability and statistics. It's one of the most useful types of functions that there is in terms of things that you see outside of the classroom. Today we are going to focus on just some basic applications of those, and as we progress further into this unit, we'll get into some more advanced applications of the function. So let's go ahead and jump into a problem here, a word problem. Problem number 8 says, when objects cool, they follow the function model T of x, where T of 0 represents the initial temperature, T of R represents the temperature of the room, T of x is the temperature of the object x minutes later, and K is greater than 0 is the cooling rate of the object. A pizza is taken from an oven at 525 degrees Fahrenheit and is placed on a counter to cool. In part A, it says if the kitchen temperature is 75 degrees Fahrenheit and the cooling rate of this type of pizza is K equal to negative 0.35, what is the temperature of the pizza 2 minutes later? So what we want to use is this function T of x, which gives us the temperature of an object x minutes after pulling it out of or moving it to a location with a different temperature. So in our case, we have an oven, and we are taking the pizza out of the oven. It's at 425 degrees, putting it in the kitchen, that is 75 degrees, and we want to figure out what the temperature is going to be after 2 minutes. So we need a function. So what we're going to do is we're going to substitute into the function of T of x. So T of x is equal to temperature of T sub r, which is the temperature of the room. So this is the temperature of the pizza after we're removing it from the oven, the new location. The temperature of the room is the new location. So that's going to be 75 degrees Fahrenheit. We are going to add to this T of 0, T sub 0, which represents the initial temperature. So if the pizza is in the oven at 425 degrees, and it's been there for an extended period of time, we're going to assume that the pizza initially is going to have that same temperature, 425 degrees. Then we are going to subtract T sub r, which is the temperature of the new location, the kitchen, which is 75, and take that result times E, we see Euler's number here, to the kx power. So k is negative 0.35, so this would be to the negative 0.35 power. If we want to simplify this, we can do 425 minus 75. So this would be T of x would be 75 plus 350 e to the negative 0.35x power. So question A asks, what is the temperature of the pizza 2 minutes later? Remember that x is already in minutes. So what we can do here is we can substitute in 2 for x and then use this to solve for the temperature. So this would be 75 plus 350 times e to the negative 3.5, or sorry, negative 0.35 times 2 power. And this would give us the approximate temperature 2 minutes later. So this would be approximately, let's go ahead and round to 2 decimals, 248 degrees, or sorry, 248.80 degrees Fahrenheit. And this is after 2 minutes. Now we could also do this graphically. We did this algebraically through a substitution. We could also do this graphically, and I'm going to go ahead and sketch the graph because this is going to be useful for us as we start to look into the question for B. So let me sketch a graph here. So we're going to graph this function, T of x, that we created. So this would again be 75 plus 350 times e to the negative 0.35 or 0.35 x power. Now, what I'm going to do with my window is I'm going to adjust the x minimum to 0 because this is minutes. So the x-axis here, let me label my axes. Sorry, here we go. The x-axis is in minutes, and this is minutes after it's been pulled out of the oven or minutes after it's been moved to the kitchen where the temperature is 75 degrees. The y-axis would be the temperature of the pizza in degrees Fahrenheit. So my x minimum is going to be 0. I can't have less than 0 minutes. My x max, we don't know exactly what this is going to be. Let me move it all the way up to 60, just in case maybe I need to answer question B. I'm going to make my x max 60 and hope that this is large enough. If not, we'll make adjustments. Then I'm going to go down to zoom 0 to zoom fit it. And this is the function that we get. So I'm going to go ahead and bring my y minimum here down to 0. Now we'll see that this function is an exponential function and it does kind of level off here. It's going to level off at the line y equals 75. We know that it levels off at y equals 75 because that is the vertical translation, and that would give us the excuse me, the vertical shift would give us the horizontal asymptote. So I'm going to go ahead and just find my y-intercept here just to give me some point of reference and sketch my graph. You don't necessarily have to put in that y-intercept, but we would have something that looks like this. Now to answer question A, I could have used my graph to answer question A by hitting second trace and going to value because I know an x value. I can type that value in and it would give me the corresponding point. So this point I would label on my graph, and I could answer the same question that we did algebraically by using the graph. Now the reason that I came up with the graph is for part B. Part B says how long until the pizza is cooled to a temperature of below or less than 90 degrees. So what we would want is we would want T of x to be less than 90 degrees Fahrenheit. So if I substituted in the equation for T of x and then tried to solve for x, I would be unable to do so because I would have the variable in the exponent, and there's, based on what we know, we don't have any way to change a integer into Euler's number. So what I'm going to do here is I'm actually going to use the graph because I know what y equals 90, or I know that y equals 90 in this case. I'm going to go ahead and graph the line y equals 90 and find the intersection. So I'm going to go to second trace intersect, move my cursor over close to the intersection here, select enter, make sure it's on the second line, select enter, and I'm not going to guess, I'm going to select enter again. So this is going to give me the approximate value here. So we're going to approximate this to 990. So the question for B is how long until the pizza has cooled to a temperature of below 90 degrees? So at 8.9996656, it is at 90. So at 9 minutes, or let's say 9 minutes or more, 9 minutes or greater, we'll give a temperature of below 90 degrees. So maybe we know that we want to eat this pizza when it's at near a temperature or below a temperature of 90 degrees to avoid burning our mouth. We know that we're going to need to wait 9 minutes once this pizza has been moved into the kitchen. So this function is, this equation is going to be useful for us. This equation again allows us to find the temperature of an object once it has changed locations and begins to cool. Let's look at problem number 9. Problem number 9 says, for insurance purposes, it is estimated that large household appliances lose 1/5 of their value each year. The current value can be modeled by the function v of t equal to v of 0 times 4/5 to the t power. where v of 0 is the initial value and v of t represents the value after t years. How many years does it take the washing machine that cost $625 new to depreciate to a value of $256? So here, what we want to do is we want to substitute into our equation. So v of t would be the value over time. V of 0 is our initial value. So our initial value for this washing machine is $625. So we can substitute 625 in for v of 0. Then we would have 4/5 to the t power. Now, we want to figure out how many years does it take the washing machine that costs $625 new to depreciate to a value of $256? So we could here substitute in 256. Now maybe we want to try to solve this algebraically. If we want to try to solve this algebraically, we would divide both sides by 625, thinking reverse order of operations to get t by itself. And so I'd have 256 over 625 equal to 4/5 to the t power. We can actually solve this one algebraically using the uniqueness property. What I may realize is I need a base to be 4/5. So I'm looking to find out if 256 over 625 is some power of 4/5. So let me just look at the 625. 5 to the 4th power is 625. So then if 4 to the 4th power is 256, and it is, I can write this fraction as 4 over 5 to the 4th power. And this would allow me to solve for t. In this case, I would find that t equals 4. So it takes 4 years for the value to reach $256. So we can actually solve this one algebraically by substituting the values that we know into the equation and then changing the base and using the uniqueness property. We could also solve this one graphically. If I wanted to solve this one graphically, I could sketch or originally start with the original function, which is 625 to the 4/5 or times 4/5 to the x power here, just using x as my variable. And then I'm going to put in the y value that I'm looking to find, 256. I'm going to adjust my window. I'm going to set my window. I'm going to put my x maximum back to 10 here, leave my x minimum 0 because I can't have less than 0 years. And then hit zoom fit, which is the 10th option. So here we have the value of the washing machine with its depreciation shown. And there we have the line y equals 256. I'm going to go ahead and give my y minimum down to 0 just so I can see all the way to the y-axis. So if you do this graphically, you would sketch in your curve, the curve that represents the depreciation. Then we can find the intersection of these 2 points using the intersection function. And it gives us the point 4, 256. So 4 represents t, which is in years. So graphically, we can get to a point where it says 4 years for the value to reach $256. So if you can do these algebraically, if you can substitute and solve these algebraically, that's definitely a method that we can choose. You can also do them graphically, as we did in problem number 8. And this looks like a good place to stop. So here are some basic applications for exponential functions. As always, thank you guys for tuning in, and I'll see you soon.